today we're going to be talking about radioactivity. First of all, these are just kind of your main definitions. Radioactive material are the ones that actually contain the unstable nuclei. Radioactivity is the emission of the energy, and then radioactive decay is the whole process. So these are just kind of important ways to kind of think about what are you talking about, the material, the energy, or the process. And so it's materials, radioactivity, or decay. Okay, so now let's get more into what are we actually talking about when we refer to radioactivity. Alright, so first of all, radioactivity is a very natural phenomenon, so it's surrounding us more than you think it is. So yes, it's in medicine, diagnostics, that might be the first thing you think about, or probably the first thing you think about is like in Japan where you had a meltdown and everybody got emitted with radioactivity. Okay, but in actuality, every day we're getting emitted with radioactivity. There is natural background radiation that's emitted just from the earth. Okay, so the question is well, why aren't we all dead then? Okay, and if you look at this table on the right, annual radiation exposure, typical amount received in 1 year in millirems, 2633, air is 198, medical, diagnostic x-rays, if you just get one, that's about 40. Okay, but if you were to get a much higher dose, that's when problems occur. And so if you're a rad tech, radiology technician, that's why you have to wear the little like pin badge thing, because it'll clock how many millirems of radiation you've been exposed to. And over time you won't be able to do your job anymore, because after you've received so much, you just can't absorb any more radiation because it's unsafe for you. Okay, so like for instance, radon-22, it's a common source of radiation, and what it is there's uranium in all rocks, and basically if you have an old basement especially, then uranium might be released in your basement to uncertain safe levels just because it's not being added to the air and being kind of swept away by fans in your house, open windows, that kind of thing. But typically that's only in really old basements and that kind of thing, and in certain places it's more common than others. So most of this, pretty much all newer houses have been swept with somebody's come in and tested for radon levels. That's what they're testing for, is to see how much radiation is seeped in from the rock surrounding your house, and your house could be sealed to help prevent any more contamination. Okay, and so this is kind of the most typical way it's used in medical imaging, is that you can use some of these isotopes that we've been talking about, and you can use them for diagnosing all these different disorders. Just because of where all the different isotopes will end up in your body, they can then scan your body and see where these isotopes ended up. And if, for instance, if all of your iodine-131 collects in your thyroid and doesn't go away, then guess what? You've got some kind of thyroid disorder. Okay, or you could actually use it to treat thyroids as well, depending on how you're utilizing it. Okay, so I just kind of wanted to make you aware of it. Read a little bit more if you want to know more. Okay. Oh, and this is also pretty interesting, is that radioactivity can be detected in plants. This one was kind of cool. Oh, I forget which radioactive release it was. It was somewhere in like Ukraine, I think is where it was. There was a whole bunch released, but the problem was there was a big body of water right next to the country, and a lot of it seeped into there, and so you couldn't fish, you couldn't go swimming in it, because if you did, you'd become, glowing. So what they actually did was they planted a whole bunch of sunflowers along the edge of the shores, and as the sunflowers grew, they absorbed the water, and guess what was in the water? The radioactivity. The radioactivity traveled up the plant, and then you can just remove the plant, you're removing the radioactivity. So that's basically one of the ways that plants have been used to help remove radioactivity. Okay, because they naturally will have the same radiation that's in their environment. Okay, and so that's one way that actually leads to carbon-13 dating, which we'll talk about here in a little bit. Okay, so there are 3 types of radiation: alpha, beta, and gamma. Basically, alpha particles, they're positive, and the reason they're positive is because they are basically the emission of a helium nucleus. Beta particles, they're negative, okay, basically because they're an emission of an electron. And then gamma, they carry no electric charge, and they're they radiate non-visible energy. Okay, so this is an overview slide, so if you want to write all this down, pause the video, that's a great idea. But we're going to go really in depth into what is alpha, what is beta, and then just kind of briefly discuss gamma. Alright, so first of all, alpha particles. If you want to get hit by any type of radiation, you want it to be alpha. Why in the world would I say that? Well, for one, it is the least energetic, okay? So it's not going to pass through paper. So if you're wearing clothing, your clothing is going to protect you from alpha radiation. Whereas unless your clothing is aluminum, beta particles are going to go right through, okay? But they're not going to go nearly as in depth into your skin as gamma particles will. So if you got hit by alpha, beta, and gamma particles, the alpha would stop at your clothing, the beta would go into your skin, the gamma radiation would go all the way through to your bone. Okay, so typically when you get the really dangerous exposure, it's because your gamma levels are so high that it gets into your bones. It does a whole bunch of destructive behavior there, particularly to your cells. Basically, cancer is caused by one form of cancer can be caused by your cells being hit by radiation, and what that does is it kind of destroys their programming. And so if your cells are no longer programmed properly, they're not going to do their jobs. Okay, so it can cause bleeding that's uncontrolled. I mean, a whole bunch of bad effects. Okay, probably one of the most painful ways to die, okay, is radioactive poisoning. Alright, because alpha particles are charged, if you were to put a magnet and send alpha, gamma, and beta through that magnet, the alpha particles would curve toward your negative end, your beta particles would curve toward your positive end just because they're both charged. Whereas gamma rays, they would just pass right through the magnet because they are not charged. Okay? Alright, so this is the really cool part about radioactivity, is what in the world causes radioactivity to come, like where does it come from? Okay, so where it comes from is the strong nuclear force. So remember we were talking about protons, neutrons, and electrons? A lot of you had really good questions. The best one in class was where we were talking about, well, there's protons and there's neutrons and they're really close together, but if the neutrons are neutral, you still have protons close together, okay? And the protons are still positively charged, and they're still going to be repelling each other, okay? Because those neutrons, they don't have a charge. So basically what I said was there's this strong nuclear force that exists. And we didn't get very much into it because, well, there's not a whole lot, there's still so much that's fuzzy, so it's not completely understood, okay? But basically, this strong nuclear force is very strong between nuclear particles, and that's what it means by nucleons. Nucleons is either the neutrons or the protons, okay? But this nuclear force is only very effective over short distances. So if it's really close to a proton, everything close to it, it's going to pull it in like glue. So it's the glue that holds the nucleus together. Whereas two positively charged protons, they can affect each other over a relatively long range in comparison. So on both sides of the nucleus, protons on both sides of that nucleus can feel the positive repulsion, okay? So what's going on here is you've got both forces at bay, okay? Because your two positive charges are going to feel a repulsion, okay? But there's going to be a strong nuclear force, which basically all nucleus particles feel it and emit it. Basically, you've got both the neutrons and the protons will both feel it, okay? And they're going to have a strong nuclear force, okay? It's going to be very attractive. So the idea here is if two protons are far apart, they're going to have a stronger repulsive force. And that's like example B, okay? Because the strong nuclear force is only attractive over short distances, so it's not going to be able to pull those two protons very well together. And so if they're further apart, their electric force is still going to be felt, and so they're going to try and push each other apart further, okay? If you throw in neutrons in the mix, they're not going to have any electric force, but they're going to have that strong attractive force, so it's really going to hold them together, okay? So whenever you're talking about all the forces at play within the nucleus, you've got both the strong nuclear force and the electric force, okay, which in this case is always going to be repulsive because you're dealing with only protons, with the electrons outside of the nucleus. Alright, so for example, whenever you got something that is, this is an example here where it's kind of showing you schematically of what we just looked at before. It's that nuclear cement that holds everything together. Okay? And neutrons specifically only feel attraction but not repulsion because they do not have a charge. Okay? Alright, so let's look at this example. In this case, part A, okay, that's something that has 1, 2, 3, 4, 5, 6 nucleons, okay? 3 protons, 3 neutrons. Okay, so the neutrons are shown here in gray, and the red part is your protons. The nucleons here are really close together, okay? So what that means is they have a really strong nuclear force. The repulsion, you know, they're not very far apart, so it's still strong. But because everything is close together, the strong nuclear force is really going to be strong and hold everything together. So that's not a problem. The problem gets to be is when you have a huge nucleus. Because remember, as we go along the periodic table, the masses got exponentially bigger as compared to the atomic number. And so once you're dealing with like uranium or some of the huge atoms, those nucleuses are big. Okay, which means that the nucleons are farther apart. So you have one proton on the outside compared to one on the completely opposite side of the nucleus. They're going to still feel that repulsion, but it's not going to feel the same nuclear cement glue from the one on the other side of the nucleus. And so what happens is as you grow bigger and bigger with that nucleus, this nuclear glue is not as able to hold together the nucleus quite as stably. Okay, quite as strongly. And so that's what I mean by this title here of an imbalance of forces. That as the nucleus grows, the nucleus is not as stable. Okay, so that's basically what radioactivity stems from, is because your nucleus is not nearly as stable. Alright, so this I think is the coolest slide ever. Once I read about this, it made so much stuff make a lot more sense. Okay? If you remember looking back at our masses of our neutrons, our protons, and our electrons were really small. Remember, they were pretty much insignificant in contributing to the mass of your atom. But the neutrons and protons were almost identical. Almost. Guess which one was slightly heavier? The neutron. Okay? So what's cool about this is the neutron's slightly heavier. Why? Because in essence, a neutron is a proton and an electron. Whenever I first read about that, it pretty well blew my mind. The idea of, oh, it's neutral because it does contain a positive and negative charge. Okay? And the cool thing about this is when you've got beta decay, what actually happens within your nucleus is that a neutron will decay into both a proton and a neutron. And so you've got that neutral charge that's essentially turning into a proton and turning into an electron. Okay? And that electron is going to get emitted. Okay, but that proton is going to stay into the nucleus. Because obviously if the electron is right there next to the nucleus, it's not going to stay in the nucleus because electrons don't belong there. Okay? So the electron gets shot off. The proton stays in the nucleus. Okay, and so this is kind of the neat thing about beta decay. It's called decay, but guess what? That bottom bullet there at the bottom of the slide, beta decay always increases the atomic number by 1. Why is that? Okay, well, let's think about two things. The atomic number, which the atomic number is always related to what? The number of protons. Okay, protons equals atomic number. Okay, but then you also have atomic mass. If a neutron changes into a proton, have you essentially changed the mass at all? No, because they have essentially equal masses. What emitted was an electron. Electrons hardly have any mass. So your mass isn't changing, but what is changing is the number of protons. Let's say you start out with 5 neutrons and 5 protons. That means your atomic number was 5 because your number of protons tells you your atomic number. Now you just had a neutron decay into a proton, so you lost 1 neutron to give you 4, but you gained a proton, so now you have 6 protons, so your atomic number just increased by 6. It's almost like alchemy. Okay, the idea is, remember this whole time I've been saying your protons do not change, your protons do not change. Well, they do if there's radioactivity present. So it's not an entire truth, but it's still almost 100% true. Okay, but the thing is, why alchemy couldn't work is because gold still has a pretty relatively stable nucleus. You have to get to much heavier elements before you really start to see this radioactivity. Okay, so beta decay. Think, the cool thing about beta decay is you've got a neutron that's decaying into a proton and an electron. Okay. Next is alpha decay. Alpha decay is what happens whenever you change one element into another element because you're releasing a helium nucleus. Okay, so in this case, uranium has a 238 is its mass. Okay, which means it has 92 protons and then 146 neutrons. Whenever it decays via alpha decay, it loses 2 protons and 2 neutrons, which are the substance that makes up a helium atom. Okay, because if you go look at the periodic table, it's got an atomic number of 2. 2 stands for protons, but it has a mass of 4. The 4 comes from the fact that there are 2 protons and 2 neutrons within a helium nucleus. Okay, so what happens is anytime you have an element that undergoes alpha decay, it's changing also to another element. It's become a new element because it's changing atomic number. Okay, just like before with beta decay, you changed atomic number. That means you literally do become a different element. Okay, so with alpha decay, you're decreasing the atomic number by 2. Beta decay, you increased it by 1. Okay, so now you're decreasing it by 2 because you're emitting, you're sending off a helium atom, and that helium atom is just being released from that nucleus. Okay, so that's your alpha decay and your beta decay. What I circled there with the helium, that's the kind of notation for alpha decay. If you see that particle being released, you know, for instance, that 100% you're talking about alpha decay. Okay. Alright, so the thing to note with these nuclear equations, what really matters is the fact that they're balanced. So if you have all the mass numbers at top balanced, you're good. Meaning 234 plus 4 gives you 238. Check. Also, the atomic numbers at the bottom also balance. 90 plus 2 gives you 92. The idea is you're not losing mass, and you're not losing the number of protons. They're going somewhere. Law of conservation of mass. Okay, so this is kind of a summary part. Alpha, you're decreasing the atomic number by 2. Beta, you're increasing the atomic number by 1. So kind of keep that in mind. This is kind of good for multiple choice questions. Is if I say you've got uranium and it's undergoing beta decay, what element did it turn into? Go to uranium on the periodic table, increase the atomic number by 1, so go to the next element to its right. You've got a beta decay. If it undergoes alpha decay, go find out uranium on the periodic table and click 1, 2 elements to the left. You're decreasing its atomic number by 2. That's what it would become if it were to undergo alpha decay. Okay? Kind of in summary, here's kind of what I mean by that. This is uranium. It's going to decay all the way to the very bottom to lead through a whole bunch of steps. So first off, uranium goes to thorium. Okay? Then it can come back to uranium and then go all the way down the arrow. Take a moment now and think about this. Is the blue arrow or is the red arrow indicating alpha decay? Okay, hint, I wrote it in blue. Okay, the alpha decay is the blue arrow because remember the alpha decay means you decrease your atomic number by 2. So look at that lower axis. Uranium is going to thorium. So uranium had a mass of 92 and it was going down to 90, so it's becoming thorium. Then it undergoes 2 subsequent beta decays. Beta, you increase your atomic number. So thorium went to palladium, I think that's palladium, and then it went further to uranium from 90 to 91 and then to 92. So the red arrow is indicating beta decay, but the blue arrow is indicating alpha decay. Okay, need to pause the video at this moment and just kind of look at that figure and figure it out just a little bit more. Alright, so in summary of that section, alpha radiation is always positive. It results in the release of a helium atom. It's an atom that emits the radiation, loses, whatever the atom is that emits the radiation, loses 2 protons and 2 neutrons. So that's why it actually does reduce the atomic number of that atom by 2. Okay? Beta radiation is always negative. It releases the electron, which comes from that neutron, which changes to a proton and an electron. The atom that releases the electron loses the neutron and gains a proton. So it, in fact, increases in atomic number. Okay, so then what about gamma radiation? Because that's the only one left. The thing with gamma radiation is it's always produced alongside and after alpha and beta radiation. So anytime you have alpha radiation, you also have beta radiation. Anytime you have, as long as you have alpha radiation, you also have gamma. As long as you have beta, you also have gamma. Okay? The idea is that when you undergo either alpha or beta radiation, the nucleus is in such an excited state that it wants to release all that extra energy in order to become more stable. So in doing so, it releases that energy as a gamma ray. Okay, and remember, gamma rays are neutral. Okay, so it can give it off as heat. Okay, or it can just give it off as a non-visible photon. Okay, so let's go back to that. Alright, so the idea here is that's why it's so able to penetrate your skin, penetrate everything but lead, is because of the fact that it's so energetic. You know, even, decomposing a neutron into a proton and electron, how crazy is that? How much energy is that going to, be released? A ton. And that energy is going to be released as gamma radiation. Okay? Alright, so now let's talk about the effects of these radiations. So what you see here on the right is a Geiger counter. Okay, so the idea here is we can actually measure this radioactivity. Okay, the shorter the half-life, the greater the radioactivity. Okay, because basically what half-life is the amount of time it takes for the sample to decompose to half of the amount it was presently at. Okay, meaning this example here, if you have 1 kilogram of it, if it takes 1,620 years to lose half of its mass, in comparison to, let's say, it took you 1 minute to lose half its mass, it's a lot more reactive if it only takes 1 minute. Okay, because that means it's trying to get rid of all that energy super fast. Okay, so the shorter the half-life, the greater its radioactivity, because it's losing so much of its mass so quickly, it's really radioactive. Okay, alright, so half-life, let's look into it a little bit more. Alright, so this is what's called isotopic dating, and this is what you see whenever you've got, you know, carbon dating, that kind of thing. Whenever you hear that, this is what it's meant by isotopic dating. Basically, whenever nitrogen is in the atmosphere, a whole bunch of stuff is in our atmosphere. Remember from that first slide, a whole bunch of it is also radioactive. So what's going on is nitrogen, but specifically the isotope of N14, is in our atmosphere. Okay? It can be converted to carbon-14 in the atmosphere. So carbon-14 naturally exists in our air. Whenever plants consume this C14, it's going to be incorporated basically into its structure. And because plants are organic, there's a whole bunch of carbon in plants. We are also organic life forms. We eat plants, or we eat animals who ate the plants. Okay, unless you're a vegetarian. Okay, so what's going on with that is you are consuming C14, and the amount of C14 that you are consuming is going to be directly related to the amount that was in the atmosphere. So the idea is with plants will continually replenish C14. Okay, what I mean by that is carbon-14 will eventually decay back to carbon-12, because carbon-12 is going to be your most stable nuclei. But if plants are continually alive, they're going to continue to breathe in and pull up carbon-14 from the soil. That C14 is going to continually to be present within their structure. Okay, so it's always going to have a certain amount of carbon-14 built into their cell and a certain amount of C12. But the second that plant dies, it's no longer pulling up nutrients from the soil. So that means you're no longer pulling up any carbon-14, you're no longer pulling up any carbon-12. But your carbon-12 is going to stay within the plant. Your C14 is going to decrease and go back to carbon-12. So that means over time, your plants will only have C12 in them. Okay? If they still have C14 in them, then that means they're relatively new. Okay, so the idea here is that you can go back and figure out how much carbon-14 is in a plant compared to the carbon-12 and date your plant. The half-life of carbon-14 going back to carbon-12 is 5,730 years approximately. So that means is if you say, let's say you have 1 gram of C14, 5,730 years ago, it would have had 2 grams of it. Okay? Alright, so the way that carbon-14 dating works is you're able to calculate the age of pretty much anything that contains carbon. If it didn't contain carbon in it, you can't date it. Half of the carbon-14 decays in about 5,730 years. So what's going on is you can go back and you can say, here's how much carbon it should have had previously. And you can then say, here's how old it is based on that. There is about a 15% error rate, and the reason for that is because how do we know how much carbon-14 existed in the environment, 10, 20,000 years ago? So how we're trying to do is we can go back, but we can only go back so far, okay? Because the idea here is eventually carbon-14 will decay so much that our instruments cannot pick up the small amount that's remaining. So carbon-14 will only work to be about, I forget, it's like 30,000 years or something. And so they have to use other types of isotopic dating if you want to go back before that. But that's how carbon dating works. It relies on the idea of a half-life, and a half-life is the amount of time it takes for your sample to lose half of its mass, basically. Alright, so here's a concept check. Try and write this down. So pause it after you read this question and try and figure out what the answer is. An archaeologist found that 1 gram of an axe handle contains 1/4 the amount of C14 compared to a tree today. Okay, so the idea is you've got a wooden axe handle and you can compare it to a present day tree, and it has 1/4 of the amount of C14. Assuming that environmental C14 to C12 is the same today as when the axe was made, how many half-lives can have passed? So you want to do is you want to start with the 1 gram of an axe handle. Okay, it contains 1/4 the amount of C14 compared to a tree today. So if we have 1 half-life, it would reduce the 1 gram to 0.05 grams. If you have 2 half-lives, so 1 half-life means you just take 1/2 of the starting point. 2 half-lives would reduce the 1/2 gram to 0.025, because you take half of the 0.5 and the 0.5 was half of the 1. Okay, 3 half-lives would be the same as half of 0.25 or 0.125. So the idea is for every half-life you just reduce the number that you had by 1/2, and that'll tell you how much mass you have after that life. So after 1 half-life, 1 gram is reduced to 0.5 grams. After 2 half-lives, it's reduced to 0.25 grams. After 3 half-lives, it will reduce to 0.125 grams. So what this is saying is, if you've got 1 gram of an axe handle, it would have 2 half-lives have passed. And so you have to figure out what the half-life of carbon was, which was on our previous slides. That means about 10,000 years have passed. Okay. Alright, we're going to watch some videos. Hopefully finish up here pretty quickly. We're going to watch this thing about rubber bands. This is the slow-mo guys, which are fabulous people with a very nice high-tech camera. And what they're going to do is they are putting rubber bands around a watermelon.
Oh, that's a good shot. Putting rubber bands around a watermelon.
And you might say, well, why in the world are they putting rubber bands around a watermelon? Okay, that's a great question. Because it's fun, and I guess they're bored. So let's see what happens.
Chipping out the top as well, and the sides. Oh, it's starting to crack everywhere. Ooh. It's perspiring.
And they're still putting rubber bands around the watermelon. Kind of see the watermelon kind of bulging.
Severed it in half. Bloody hell. When? Severed it in half. Oh my god! Wow! Oh, that's incredible! Oh my god!
I love the rubber band ball that's traveling. Alright, you may be saying, why is she showing me this? Okay, well the reason I'm showing you this is I think this is a great example to think about nuclear fission. So what happens with nuclear fission is you're literally splitting a large nucleus into smaller halves. Alright, so the idea here is that when you've got a really large nucleus, it's pretty unstable. Sort of like that watermelon. It's sitting there with a lot of mass. Then, whenever something hits that nucleus, and in this case it's going to be a neutron that's ejected from previous samples, and we'll look at that in a minute. But once it collides with it, see how the uranium atom at the bottom of the screen is kind of circular depicted, but then it gets elongated. Okay, it deforms it. Remember looking at that watermelon, how it kind of started to squeeze in? Go back and watch it if you need to. It's a fun video to watch. But it starts to squeeze it. And eventually those rubber bands squeeze that watermelon so much that the watermelon couldn't hold on any longer. And it exploded. And yes, it releases enormous amounts of energy. Okay? In the atomic scale of things, what's going to happen is that uranium atom at the very bottom is going to be split in two into 2 new atoms, both atoms being significantly smaller than the starting atom. But even more so, it's also going to release a couple of neutrons, okay? So if it releases 3 neutrons for every starting atom, each of those 3 neutrons can go on and collide with a new nucleus, make those watermelons split in half, which will then make 3 more shards of watermelon, which will then split 3 more watermelons. So before long, we're all covered in watermelon goo, okay? And that is nuclear fission in a nutshell. 7 million times more energy than a TNT explosion is released from that nucleus just getting ripped apart, okay? All of that energy is just being released into everything around it. So that's fission. It's called a chain reaction because when one nucleus splits in half, it produces 3 more neutrons. Each additional neutron goes, and if it collides with another atom, then guess what? Even more are going to be produced. So I have another video from this one, and this one is also on YouTube. This is called a mousetrap reactor, and this is basically what happens when fission begins. Try and stop that right now. Oh wait, you can't. Okay, there's still a couple mouse traps exploding every now and again. Alright, that is a mousetrap reactor. That's what happens with fission. So go through, read the book, think about how much energy is produced by a fission reactor. Do you think we should use them instead of coal? Think about the pros and the cons. So you've got obvious pros that are, oh, so much energy is produced. Okay, for every uranium atom, how much energy is possible? So much. Okay, you've got what's called a critical mass, though, where after you get your uranium, and if you put too big of a chunk of uranium, you can basically make that reaction unstoppable, and that's what could happen in a meltdown. Okay, what are the pros and cons? Think about radioactive waste. Think about meltdowns. Okay, think about all those things and kind of think about what you would actually recommend if you were, Department of Energy and you were the big wig in charge of everything. What would you recommend the United States do with our energy shortage? Okay, really interesting research. There's no real answer, I don't think, to this, but there are definite pros and definite cons. Then the last concept we're going to talk about is fusion. So fusion is brought about by high temperatures. If you don't have high temperatures, you can't have thermonuclear fusion. What's going on here is they're initiated sometimes by a fission reaction. So if you have one nucleus that is shot off by fission, one neutron that is shot off by fission, it can collide with another nuclei. When there's enough high energy of these nuclei that are being produced by fission, the individual nuclei will go on and recollide with other nuclei that were created. And when 2 nuclei collide, not a neutron in a nuclei, but 2 nuclei, they collide, they release a whole bunch of energy as photons of light. Okay, and that's basically how we get all the light on Earth. Is all this light is being produced by fusion in the sun. It's being released as photons of light. It travels all the way here, and we get to survive and live another day. If we could harness this energy, wow. But we haven't done it yet. Okay, there's a whole bunch of thoughts out there of how we could theoretically harness this energy, but as far as I could tell, there are currently no commercial fusion power plants in use, just because the idea of it going critical is very probable. So they haven't figured out a way to really control it, so we haven't figured out a way to harness the energy. Okay, so kind of in conclusion, what is an alpha particle, beta, gamma? What are all of those things? How harmful are they? What are they produced by? Etc. Same thing by nuclear fission and nuclear fusion. How are they different? Okay, nuclear fission, you have a neutron colliding with a nuclei. Nuclear fusion, you've got 2 nuclei colliding together. And then half-life. How does half-life tell us about the amount of radioactivity and time that has passed?